Okay, so today we will be discussing how a continuous time periodic function or signal can be represented by Fourier series. In fact, this has been discussed in your math course. Although they did not, for example, refer the functions with respect to some sort of practical signals, but still the mathematical technique is same. What I have discussed earlier, that in your mathematics course, teacher usually taught you the trigonometric form, isn't it? Can you see the trigonometric form here?
Yes, sir.
So this is what the trigonometric form actually, okay? You see that no matter in which, by which ways your constant terms are defined, but mathematically they are same. Okay, when we use trigonometric form, actually trigonometric functions such as cosine and sine omega t are real functions, and they will be associated with some Fourier constants, say bk and ak. They are also real, but they are the function of harmonic number k. And you see that the harmonic number starts from k equal to 1 to infinity, and we get a constant term there. Depending on the type of your signal, sometimes this constant term may or may not be present, okay, depending on the symmetry condition of your function or signal. This constant term refers to the average value of your signal. If you have an odd function, this average value will not be present. And you know that for your odd periodic functions, this constant will also not be present. The reason is that when we multiply an odd function periodic with a cosine function, this is an even function, isn't it? A cos is even or odd?
Even.
It is even. So if we multiply a periodic function that has odd symmetry with an even periodic function, resultant function will be what? Odd. So if you have an odd function that is periodic, then this integral over the one period would be equal to 0. But this will exist. For this reason, if your function is an even odd function, average value of the odd function is 0, as well as this coefficient will not be there. So we will have only a coefficient and sign terms. Similarly, if you have an even function, the reverse is true, okay, where your bk constant will be available, no ak constant will be there. But we generally prefer the exponential form of Fourier series. This exponential form can easily be derived from a trigonometric form by using Euler identity. Okay, you simply replace your cosine term by e to the power j. What happened? Is it okay?
Yes, sir.
So you can go from this trigonometric form to this exponential form very easily. You know that your cosine k omega 0 t is equal to what? Half e to the power minus j omega 0 kt plus e to the power j omega 0 kt, isn't it? Similarly, if you have your sine k omega 0 t, you can write similar expression. Okay, having this thing replaced by this Euler identity, you can easily derive this relationship, and this is left to you to be done. Okay, so when we represent our periodic functions by trigonometric series, you see that k value ranges from k equal to 1 to infinity, and k0 refers to the average value. It may or may not be present in a signal. But when we express the Fourier series in complex exponential form, you see your signal is real, but we are using a complex exponential to represent it. Then what will happen? Your x should be appearing as complex conjugate. If it is should be the complex conjugate, then k should range from minus infinity to infinity. It also contains the average value. If your signal, depending on the symmetry condition of your signal, that average value may or may not be present in your case. Okay, we will be using exponential form mainly in our case. The reason is that we have another class of signal that are not aperiodic. For the aperiodic cases, we have to use Fourier analysis that we call Fourier transform. We can easily go to Fourier transform if we use exponential form of Fourier series. So with this mathematical thing, let us apply this thing to some signals, and then we will try to investigate the properties of the Fourier constant for the case of CT periodic signal. Okay, this derivation is there. How can we commute between exponential and trigonometric form, and what is the relationship among AK, BK, and XK? Okay, consider a very simple periodic function. Is it periodic or not?
Yes.
It is periodic. What is the period of this periodic signal?
2.
Period of this periodic signal is 2. Okay, although we are not using unit, but this can be second, or you can consider it as second. Okay, and your signal can be volt or current depending on where you are applying it. Now, this is an exponential periodic signal. The equation of this exponential curve is also shown. Now the thing is that if we want to go through our trigonometric form, then both the constant will be present here, isn't it? Because this signal is odd or even.
It's neither odd nor even, sir.
This is neither odd nor even. If this is neither odd nor even, then both your AK and BK constants are present. But we are not using trigonometric form. We are using, say, exponential form. In the exponential form, we have only one Fourier constant xk. And that xk equal to what? That xk is equal to 1 over t, the time period, integration over 0 to t over the time period, signal multiplied by e to the power minus j omega 0 t k dt, where k is your harmonic number, omega 0 is the fundamental frequency, angular frequency defined by 2 pi over t, where t is the fundamental period of your periodic signal. Now with this thing, in your case, your period t equal to what? 2, isn't it? If your period is 2, then omega is equal to pi. So we have our omega equal to pi. Then this general equation will take this form. T equal to 2, integration from 0 to 2. This is your signal. This is what your exponential term e to the power j omega 0 kt. Then anybody can evaluate that integral. The value of this integral is this. And you can easily see that, okay, the basic difference between the Fourier constants of your discrete time signal and continuous time signal is, in the discrete time periodic cases, your xk is also periodic in k, and the period number is exactly equal to the period of your original discrete time signal. As a result, we only need, for example, such number of distinct values of xk that is equal to the period of your discrete time signal. But in the case of continuous time periodic signal, your k ranges from minus infinity to infinity, and k are integer. As k is your integer, non-integer harmonic doesn't exist. So if we plot, for example, xk with respect to k, then it will take the form of a discrete sequence of values for each value of k. K is an integer. And like your discrete time case, your signal, the value of xk for continuous time case is also complex. it will have a phase factor value as well as an what you call magnitude value. So if we plot magnitude with respect to k, it will be your magnitude spectrum, and if we plot phase with respect to k, it will be phase spectrum. And you can easily identify here that the magnitude. Okay, can you calculate the magnitude of this xk equal to what? Magnitude of xk. Magnitude of sk equal to what? It is 1 minus e to the power minus 4 divided by square root of
Root over 4 square.
60 plus 4
4 k,
pi
k
square
square
k.
pi square.
Is it okay? And you can easily see that the value will be maximum at k equal to 0. That means the DC component value will be maximum. Say this value will be equal to what? This value will be equal to 1 minus e to the power minus 4 divided by 4. All other values are the decreasing function of omega, isn't a decreasing function of k, are not they? In both
Yes, sir.
okay, in your negative k, in your positive k, this is the negative values, and these are the positive values. In both ways, this is k. And you see that the magnitude of xk is also the even function of k. Why that should be the even function? We know that a real signal is being generated by using complex exponential. So your Fourier constant will be appearing as conjugate pairs. If they are conjugate pairs, their magnitude will be same for a particular value of k. For example, say k equal to 1. If this is the magnitude, then for k equal to minus 1, the magnitude should be same. But their phase angle should be what? If one is positive, another should be
Negative, sir.
negative in order to have your conjugate. Okay, conjugate because your x for positive values of k will be the conjugate of x for negative values of k. So this is what the behavior of xk for continuous time periodic signal. We will have theoretically infinite values of xk. But in the case of periodic DT periodic signal, only the distinct values of k is equal to the number of periods of your number of samples in the period of your signal. Okay, this plot is there shown. Okay, if we plot the magnitude, your upper figure is the magnitude spectrum, and your lower one is the phase spectrum. You can easily identify that the phase angle in the positive values of k is negative of those of your negative values of k. Otherwise, they will not form conjugate pairs. So with this thing, few information can be extracted. Whenever we are using a signal, we can easily understand what frequencies are present there. Although the values of at the larger value of k, that means higher frequency component will have progressively lower amplitude. For this reason, when we are designing a system to handle this signal, theoretically infinite bandwidth will be needed. The reason is that the value of k is infinity, theoretically. As a result, infinite components of frequencies that are integer multiple of omega 0k or equivalently f0k are there in your signal. But you cannot design any system that can handle this infinite bandwidth. But we do not need in practice, okay? You will see that in compare with the lower frequency magnitude of the lower frequency component, the higher frequency component will have progressively smaller magnitude. As a result, you can truncate, for example, your frequencies, some of the high frequency components of your signal. Then your bandwidth of your signal will be limited, and you can handle it and design your system accordingly. And this is one of the most important objective of Fourier analysis that cannot be seen in the time domain, okay? So if we have our time domain, but some other perspective are there in designing your discrete time system, and that will be the content of your higher order course that we call digital signal processing. Okay, like our, okay, with although some example, a simple example is there, but you have, you can pick some problem from your book of this type, and then you can practice how to calculate the Fourier constant and how can you plot them. Okay, but in your class test or exams, your problem will be of different type, but they will not different type, they will be same type, but not exactly equal to what you are seeing in your book. So, but the equation that you are using, it will be there, you can use very simply. Now, your another signal, okay? This type of signal we have seen for the case of discrete time Fourier series, where we used an impulse train, because the impulse train is also a periodic function. And that periodic function can again be represented by complex exponentials that we have seen there. And we have also seen that the Fourier constant xk was independent of the value of k, and it was equal to 1 by n for each value of k. Okay, let us examine an continuous time impulse train, and let us analyze it, how it behaves in the frequency domain. Okay, is it not a periodic signal? Because if we plot it for each value of L, you will see that for L equal to 0, you have an impulse, but a difference is there between your continuous impulse and discrete impulse. Because continuous impulse has magnitude equal to what?
1.
For continuous case?
No, sir. Continuous case
Infinite, sir.
is
Infinite,
infinite.
yes.
Discrete case is 1.
Discrete case is 1, yes. So that's why we are using the arrow, okay? That arrow indicates that actually delta t cannot be handled as it is. It should be either integrated or differentiated associated with some other functions, okay? So these are the impulses. If we plot this equation, it will take this form. You will see that it is also an impulse train and a periodic function, because the impulses are recursively appearing after a finite interval of time. And in this case, it is say 4 seconds or something like this. Then you can easily identify that your period of your periodic function is 4. Then if you want to find the Fourier constants of this Fourier periodic function, then you can use the same equation xk, 1 divided by t, 1 divided by 4. Your integration is done between -2 to 2 over one period, say from this point to this point. Actually, the thing is that you see, Fourier, because we are integrating over one period, and your signal is localized. That means it is present at a particular instant of time within that period. So that integration, if we take the integration from -1 to 1 or from -2 to 2, it will have the same value. For this reason, we also can express our xk, xk in the general equation as 1 divided by t from minus t by 2 to t by 2. T by 2 xt e to the power j omega 0 kt. In this way, you can do that, okay? Because if your impulse is not there within this period, what will happen? The integration will be equal to what? For example, if someone will integrate it that doesn't, with a limit that doesn't contain the impulse, the value would be equal to 0, isn't it?
Yes, sir.
So this is by using the shifting property, you can, we know that if we integrate, for example, within this limit, a function something like this dt, the value equal to x0. That means the value of your signal at the location of your delta. In the same way, in our case, our delta is located at t equal to 0. So this value equal to value of this function at time t equal to 0. So this is actually, if you want to write it more clearly, it is actually something like this: j k pi by 2 to 0, something, as this is equal to 1, so it is equal to 1 by 4. And omega 0 is equal to 2 pi divided by 4 is equal to pi divided by 2. So what important thing is there, you see that like your discrete time case, in the case of continuous time impulse train, your Fourier constants of the impulse trains are independent of the value of k. If these are independent of the value of k, you see that if we want to plot it, for k equal to 0, it is 1 by 4. For this signal, for k equal to 1, it is also 1 by 4. K equal to minus 1, it is also 1 by 4. So if this is the case, then what it is happening that this, and it is real, isn't it? Isn't it?
Yes, sir.
It is real. So if it is real, then our Fourier term will be appearing in this way. That say for k equal to, say we are considering say k equal to say minus 1, 0 and 1 only. Then how many terms will be there? If you want to reconstruct the signal xt, then our reconstruction equation is equal to what? Sum over k equal to minus infinity to infinity xk e to the power j omega 0 kt, isn't it? In our case, we are considering only three values of k, say minus 1 to 1, and our xk is there. This is e to the power minus j pi by 2, because omega equal 0 equal to pi by 2 into kt. Then how many terms will be there?
3 terms.
3 terms. But each of the value of xk equal to what? Is it not equal to 1 by 4?
Yes, sir.
Because
Yes,
it is
sir.
independent of the value of k. Then this equation would be equal to what? This would be equal to what? 1 divided by 4 into, for negative value, e to the power j pi divided by 2t plus, this is not minus, okay, 1 divided by 4 plus 1 divided by 4 with k equal to 0, this term equal to 1 plus 1 by 4 e to the power oh, why it is minus? It is plus, okay. So this should be minus. Then this is plus j pi divided by 2 t for k equal to 1. Okay. So these three terms are there. Now, can you combine these two terms?
Yeah. Yes, sir. By a cost terms.
Cost term. So your xt can be now what? 1 divided by 4 plus half cosine pi divided by 2t, isn't it?
Yes, sir.
Fine. Now, if we consider, for example, this is equal to say 2 by 2, then how many terms are will be added now? Again?
5 terms.
5 terms. Okay. With this 5 term, we can add another cosine term there. It will be equal to 1 divided by 2. Can you tell me what will be the frequency? Because
Sir,
the
2
value
pi by
of k
2.
is equal to 2. So it will be equal to pi by t, isn't it?
Yes, sir.
Fine. Then if we add another, again further 2 terms, then it will be equal to what? Half into
3 pi by 2.
cosine 3 pi by 2, exactly. Then can you verify this, not 3 pi by 2 actually, 3 pi by 2. Okay. Now you see that if we add all this together, it will generate an impulse train, isn't it?
Yes,
Because,
sir.
okay, then try to take this as a practice. Okay, you use you can write your MATLAB code. Okay, add, for example, say consider you can vary the value of k from k equal to -1 to 1 to k equal to say -100 to 100. Okay, then you generate this signal, add them together and plot it, and if possible show it to me in the next class. Okay, that it is taking the form of an impulse train. You got it? Then
Yes, sir.
you will understand that an impulse train mathematically can be generated by using cosine function. Okay, a periodic mathematical impulse train can be generated by using cosine functions. Okay, try to verify it. You understand what is your task?
Yes, sir.
Okay,
Yes, sir.
okay. So you change the value. Okay, if you can write a general MATLAB code, then it is simply you can run the loop. Okay, for variable values of k, that will give you an idea how your signal is gradually getting the shape of an impulse train. Okay. So another thing, similar thing we have discussed earlier for the case of discrete time signals. Okay, if your signal is a general type of what we call periodic signal, then we can use this mathematical technique to extract the frequency information of the signal, because this cannot be seen in the time domain. But if your signal is itself is given in the form of sine and cosine functions, and they are harmonically related, we can easily determine what Fourier constants are there in the exponential form actually. Because for example, say if we have a sine term only or cosine term only, this equation, then it has a single term, isn't it? You can easily calculate what is the frequency of your signal, what is the time period of your signal easily. And in the trigonometric sense, we have only one term there, isn't it? You can consider it just a single frequency, your Fourier amplitude equal to 3, something like this. But if we want to express it into exponential form, then how many Fourier constant will be involved there?
One, sir, only.
One, because you have to express it into exponentials. Then your signal will be equal to what? Your signal will be equal to, because you know that if this signal will be equal to 3 divided by 2 into e to the power minus j pi divided by 2t plus pi by 4 plus e to the power minus plus j pi divided by 2t plus pi by 4, isn't it? By
Yes,
using
sir.
Euler identity. Then can you extract the Fourier coefficient from here? You separate your cosinusoidal e to the power j omega t kt type term. That will give you the coefficient of that term is the Fourier constants. So this is equal to what? It is equal to 3 by 2 first term e to the power say minus j pi divided by 4 into e to the power minus j pi by 2 t. You know that your omega 0 equal to pi by 2. If it is omega 0 equal to pi by 2, for this term, what is the value of k? Is it not k equal to -1?
Yes, sir.
So then this is the coefficient of this term for k equal to -1. This quantity is equal to, is it not x minus 1? The value of your Fourier constant for k equal to -1.
Yes, sir.
In the same way, you will have the second term. Second term will be equal will be for k equal to +1. So we'll have two Fourier constant there, and they are conjugate to each other. If they are not conjugate, then cosinus term cannot be generated. Okay. So in this way, you can find the what? You can find the Fourier constant by inspection. For example, if this problem is extended in this form, say it is 4 into say sine pi t plus say pi divided by 2 pi divided by 2 or something like this, or nothing is there, something like this. If we have another term added with it, then how many Fourier constant we will have in exponential form? Your sine term will give you 2 and your cosine term will give you 2, isn't it? But altogether, how many things are there? Okay, you see that you cannot add, for example, a term arbitrarily with this signal. The reason is that if we have to add a term in such a way that they are harmonically related. Harmonically related means what? The higher frequency will be the multiple of k, isn't it? Here k is an integer. Then you have to find the, after adding these two terms, you have to find the resultant frequency, that what is the periodic, what is the fundamental period of the combined signal. Then accordingly, you proceed with calculating your Fourier constant. Okay, the example is that we have discussed is plotted here. Okay, two values of xk and their phase angle. You know, phase angle associated with them was one was pi by 2, another was minus pi by 2. Okay, with this thing, let me just discuss few things by using whiteboard. Look, actually in Fourier analysis, you see for periodic function, for periodic signal, the frequency content of your signal is what? An integral multiple of harmonic number. Or this is in radian case, but if we write in hertz, then it will be equal to f into k. So your k values are what? Integer. If they are integer, then what is actually happening that when we analyze it in Fourier series, your frequency information and their amplitude is contained, for example, in this constant. It is the function of k. And this xk is actually a discrete sequence with respect to k. What we have seen there, if we plot them, say this is your k, in the earlier example of exponential periodic signal, you have seen that the values are something like this. Magnitude, okay? Your phase angle can also be plotted something like this. Okay, so if this is your magnitude of xk, capital X, is it not a discrete sequence of numbers with respect to k?
Yes, sir.
Okay. When we expressed our discrete signal in time domain xn, we expressed it in this form, k equal to, but do not confuse with this k and that k. We can write another variable there, say p. Say p equal to minus infinity to infinity. We can consider it xp into delta n minus p. In this way, we can represent a signal. That means a weighted sum of impulses. As in the discrete case, the discrete impulse value is equal to 1. So whenever a signal is appearing, say for at say n equal to minus 2, the signal value is x minus 2. That x minus 2 can be also be written as delta n plus 2. That will not change the value of your signal. This is valid for discrete time signals only. The same technique can also be used in Fourier constants to represent the magnitude or phase angle of the Fourier constant. In this case, this xk sequence, magnitude of xk, this is a sequence with respect to k, will have a value, for example, at k equal to 0. That value can be written as delta k. Similarly, this value can be written as delta k minus 1. This value equal to what? Delta
K plus 1.
k plus 1. So in this way, that magnitude can also be expressed in this way. Okay, say L equal to minus infinity to infinity. We can write magnitude of x k, that means xl, into delta k minus L, isn't it? That means you can also express your Fourier constant as an weighted sum of impulses, and that impulse must be discrete, and it is discrete, where your k is the discrete variable. In the time domain case, your k is your sample number, but in the frequency domain case, your k is your harmonic number, okay? And there must be, the harmonic number is an integer. So in this way, yeah.
So only the magnitude will be associated, the phase angle.
Phase angle will also be associated. Phase angle will also be associated. Okay, phase angle will also be associated. Yeah. It is simply, you can write it magnitude equal to, okay? But you can also write similar type of equation for phase angles, okay? But if your phase angles by some way or other can be associated with the magnitude, then still we can write in this way. For example, say, if we have your magnitude, for example, xk, and with a phase angle equal to, say, theta xk, then this is actually, if we apply this thing with a delta, say, k, no, this is, let me write it again. Choose, for example, this, for a particular value of k, say k equal to L. This is your magnitude. Then we associate the angle, say, theta. Let us write it L. So this will constitute your XL, isn't it? You understand the thing?
Yes, sir.
Magnitude and the phase angle are, it is written in the, it is which form? It is written in the polar form, isn't it? Polar form. Then if we can write this thing in this way, then that is equal to this, then you can associate your delta KL there, just to represent the whole all information of your xk. Here in this case, your xl become a complex number, isn't it? It becomes a complex number. But the location where we have considered our magnitude, we also consider our phase angle at the same location. So this in your earlier equation, you can separately write it by using magnitude or by using phase, and can combine them together to write into a complex form. Okay, we will be illustrating this thing by using an example. So in this case, what will happen, rather than a real thing present there, we will be using a complex thing associated with that particular impulse function that signifies the location or the harmonic position of your signal. So sometimes figuratively it can be given, or in other cases by using mathematical expression, by using this impulse function. Okay, this is a problem from your book. Okay, I skipped few problems. They are very similar to what we have illustrated earlier. Try to solve them to get accustomed to it. It is problem 3.9a, practice problem. Okay, your xk values are given, okay? and it is for continuous time signal. For discrete time signal, actually, at least one period of your xk value must be given, otherwise you cannot generate your signal. Okay. Something is wrong there. That must be plus. Okay. This term should be k plus. This should be equal to. Oh, this pen needs to be calibrated probably. Okay, a plus sign would be there. Okay, because if both are minus, this is meaningless. Okay, in this case, you see your xk is represented by impulses, and the impulses in k. The coefficient associated with the impulse at the value of xk, are not they? So you can easily identify that these are the values of xk. Oh. Am I connected or disconnected?
Nothing is showing in the screen.
Can you see it now?
Yes, sir.
So what is there? Just we are, for example, this term should be plus. Okay, k plus 2. Look, then the coefficient associated with each of your delta are what? These are the values of your Fourier constant. Then how many Fourier constant we have? We have 4 Fourier constant. One is at k equal to 2. Another is at k equal to minus 2. This term is k plus 1, k plus 2. This is your k plus 2. So this term is k plus 2. This is your k plus k minus 2. This is your k minus 3. This is your k plus 3. So this is what the magnitude of xk. And the phase of xk is what you see that you have your two values there with phase value at k equal to minus 3, phase angle is 0 because this value is real, isn't it? These two values are real, are not they? So your phase angle is 0. But at k equal to minus 2, we have a phase angle equal to pi by 2. And for k equal to 2, you have a phase angle equal to minus pi by 2 because j is equal to what? J is equal to
minus pi by 2.
e to the power j pi by 2, isn't it? J is equivalent to 90-degree phase shift. So your phase angles are there, your magnitude are also there. Then how many values of xk we have? We have 4 values of xk. Then how many term will be present there in our Fourier sum? Only 4 term is present. We do not have anything for k equal to 0. That signifies that this signal may be an odd signal. Now, if we want to write our sum, then we have our 4 terms. This is for k equal to minus 3. This is for k equal to 3. And this is your k equal to minus 2, k equal to 2. You put the value of your x minus 3. X minus 3 is equal to 2. Your x plus 3 is also equal to 2. Your x minus 2 is equal to plus j. And your x plus 2 is equal to minus j. Your plus j and minus j, you can replace it by exponential terms, or you can keep there so that you can convert them into cosine a sign formed by using Euler identity. Your first at k equal to -3 and k equal to 3 will generate a term equal to what? If we combine these two terms, it is it not equal to 4 cosine 3 pi t? If we combine our
Yes,
first,
sir.
then if we combine our middle two terms, then it will give you sine or cosine?
Sir, sine.
Sine, yes. So you know this thing. Then by Euler identity, you can easily find that your signal will be a real signal, and that signal can easily be expressed in the form of sine and cosine functions. Ah, mm. Okay, this is what your signal. And you can easily identify that whether this signal is odd or even. You can verify it, or neither odd or not even. Now, another problem. Okay, it is also from your book, problem 3.9b. Okay, in your 3.9b, you will see that this figure is the value of your xk is given in the form of a figure with their phase angle. Okay, then in this case, 9 values of your Fourier constants are given with magnitude equal to 1, and the phase values are linearly changing from 2 pi to -2 pi for each values of your n. Then you can sum this thing up to find the value of your signal. Okay, try to do it by your own. Your value of your xk is given. The magnitude of xk is this. Magnitude of xk is this, and this is what your phase angle. You see that your phase angle is linearly changing actually with respect to k. That means if your phase angle is given there at k equal to 0, it is 0. For k equal to -1, your angles are positive. It is going in this way from -4 to, for example, +4. Okay, so your phase angles are given there. A magnitude is constant from k equal to -4 to 4. Then this is what you sum. Then this is what you sum. Okay, then you change the variable so that your sum can be taken from 0 to 8. Then you can use your general formula, this formula, just to write the equation into a closed form. Very difficult. Huh? So another problem is also there. Try to solve this problem. Okay. Now I will be discussing few things that will be very helpful. How can we apply this Fourier series, for example, in our, although we will be discussing about more about the application later, but at this point, just I am giving some hint about it, how we can use our Fourier analysis there. Okay. What we have seen earlier, another issue is that we have another square wave they are given. Okay, you try to derive equation 3.23 by your own. Okay, and let me know that you are successful. Then you can go up to equation 3.24 just to know about another function that is called sinc function or sine function. Have you seen this type of function in your earlier classes? That a function fx is equal to say sine x divided by x type function.
Yes, sir.
What is the name of this function? This function is sometimes called sampling function, okay? If we plot this function, how will it look like? If we plot this function, what is the value at x equal to 0?
Infinite.
Infinite value. This will be infinite.
1, 1.
X equal to 0. It is simply 1, okay? That this function has this shape. Okay, and this has a very wide applications in many of our communication engineering. This is called sampling function, okay? Then another function of this type is called sinc function, SINC, and this is usually expressed as the sinc u is equal to something like this. It's a sine pi u divided by pi u. Okay, how to derive this function from this function, okay? By changing some simple variable. This is there expressed in equation 3.24. So you try to redo the example Fourier series of a square wave of example 3.13, very simple. And you will see that the result of xk can be expressed into a form of this function. And from this point ahead, we will discuss in the next class. But now I am going to show you how to apply this thing in our practice. Okay, so with this thing, I will refer another book to you. Okay, not a new book, you know this book. If you have your Sadiku's book with you, 3rd or 5th edition, you go to your Fourier series chapter. Okay, there is a chapter there, Fourier series in Fourier transform and Laplace transform also. You go to your Fourier series where you will find the trigonometric Fourier series mainly, and how your Fourier series can be applied into a circuit analysis. Some problems are there. Okay, I will be showing a general perspective of the thing that we have to use for analyzing our LTI system when a periodic signal is used as an excitation or input. Look, what we have seen, although we have discussed the thing, but again I am revisiting it. It will be very important for your class test also. For example, this is your LTI. Then what we are usually doing, we are considering that we have an xt input. That xt has been expressed in this form. K equal to minus infinity to infinity xk. Xk is the Fourier constant, e to the power j omega 0 kt. This is your signal then. This is equivalently equal to what? That means you are splitting your signal into infinite number of constituents, and these are the sinusoids or complex exponentials. Then corresponding output is, you will see that your corresponding output would be equal to a transfer function at the frequencies of your input signal. It is j omega 0. This will be the function of j omega 0 k multiplied by e to the power j omega 0 kt, and you have to sum it over from k equal to minus infinity to infinity. That will be your output due to that periodic signal. So, and again, you can okay. This is correct. Can you identify what mistake I made?
Sir,
Actually,
impulse.
no, not impulse. Actually, this expression was derived when we consider that our xt is equal to e to the power j omega t or something like this. Okay, no coefficient was there. That is considered, no coefficient means coefficient was equal to 1. But as our system is linear time invariant, So if we multiply our input by an amplitude factor xk, that amplitude factor will also be there, okay? So actually, if you want to write it correctly, then your correct expression should be h j omega 0 k multiplied by xk, okay? Then this quantity h j omega 0 k into xk. Okay, when we derive the relationship, we consider the signal as e to the power j omega t. Then we define a function h j omega is equal to integration minus infinity to infinity h tau into e to the power minus j omega tau d tau, something like this. But this is called frequency response or transfer function for all frequencies. But as our input contains frequencies that are in integer multiple of omega 0 k, you can consider that your omega is now discrete. Then we can replace our omega by omega 0 k so that your transfer function will exist for the frequencies that is present in your input signal, because if your input signal doesn't contain anything with a particular frequency, there is no any meaning of that transfer function, okay? So your transfer function, it is the frequency of function of frequency, but that will exist for those frequencies, those are present in your original signal. Now, you will see that we are finding another discrete function. That discrete function is the multiplication of your transfer function at the harmonic frequencies with the corresponding Fourier constant. Then we can write, for example, this constant as yk equal to. Then your output can be then expressed as sum k equal to minus infinity to infinity yk into e to the power j omega 0 kt. Okay, now you compare your output series with the input one. You see that when we express our periodic input x as an exponential form of Fourier series, then we will see that by the concept of our transfer function, we can easily find the Fourier series of our output, yt. So your yt will also be periodic and the Fourier series is there, and the Fourier constant yk would be equal to the multiplication of the transfer function at that harmonic frequency with the corresponding value of Fourier constant of your input. So your yk can be determined in this way. So if we have a system given, with this system you can find your transfer function. After finding the transfer function, you express your input in Fourier series and try to understand what frequency or what harmonics are present there. Then we can calculate the corresponding output Fourier constant yk by multiplying our xk with h j omega 0 k. Let us illustrate this for the case of an RC filter, okay? You know that you have an RC filter, something like this. We are taking the output yt from here, your input is xt, and this is your R, this is your C. We have seen that the transfer function of this circuit is equal to 1 divided by RC divided by j omega plus 1 by RC, isn't it?
Yes, sir.
So if this is your transfer function, now if your input, for example, is expressed as xk e to the power j omega 0 kt with some k equal to minus infinity to infinity, then the corresponding hk would be equal to what? Your hk would be equal to a j omega 0 k, isn't it? Would be equal to 1 divided by RC divided by j omega 0 k plus 1 divided by RC. This is what the value of your transfer function at the harmonic frequencies omega 0 k. Now, if your xk is known to you, then your yk is equal to what? Your yk is equal to simply hj omega 0 k multiplied by xk. For example, in your previous first example of periodic signal that we have seen, that an exponential periodic function, our xk was determined as 1 minus e to the power minus 4 divided by 4 plus, can you remember, j 2 pi k, isn't it?
Yes, sir.
Then if we apply, for example, this signal, exponential signal, okay, periodic signal as an input, the corresponding value of xk we determine this. And you have been asked to calculate the output for, say, magnitude of the output say for k equal to 3. How can we find it? That means output due to third harmonic. Then magnitude, is it not, for example, yk, magnitude of yk is the magnitude of your third harmonic,
Yes, sir.
Yes, sir.
and that is equal to what? Magnitude of h j omega 0 k into magnitude of xk for k equal to 3, isn't it?
Yes, sir.
Yes, sir.
That's why you put the value of k there equal to 3, find the magnitude. Then put the value of k there, find the magnitude. Your RC must be given, otherwise you cannot calculate numerically, isn't it? Then you multiply these two things together to find the corresponding yk, magnitude only, but phase angle can also be determined. Then that will give you the magnitude of the output at that particular harmonic frequencies, okay? And you can easily identify that your transfer function is also a decreasing function of k, and your xk is also decreasing function of k. As a result, gradually the higher harmonic components will be attenuating, for example, with a faster rate, and that's why this circuit is a low pass one. Okay, the higher frequency will be getting progressively smaller, isn't it?
Yes, sir.
Yes,
So,
sir.
okay, try to do it. If you can have your computer, you can also plot this and try to explore how things are happening there. Okay, so with this thing, I want to close my lecture today. That we will be going from this point ahead in the next class, inshallah.